This is part 2 of the video notes for Objective 4, Graphing Trig Functions. In part 1, we focused on graphs that involve amplitude and an adjustment in period, or frequency for a trig function. For this part of the video, we're going to talk about the other two transformations, phase shift and vertical shift. So let's bring back our formula. Now the first time I wrote the formula, I used sine. So this time I'm going to use cosine because the formula applies to both, or really all, trig functions. A is the amplitude. B is often called the frequency and is used to calculate the period. C is the phase shift. And D is the vertical translation or vertical shift. Now, let's hone in on just phase shift and vertical shift, now that we're already established with amplitude and frequency. When we talk about phase shift, it's important to note that there's a negative embedded in the formula itself. So, if the shift is left, we know that C is negative. If you input negative C in the formula, you would be looking at f of x equals a cosine bx minus negative C. Well, we know from algebra and arithmetic with integers that two negatives makes a positive. What that means for us when we're graphing is that if we see a positive or a plus sign in our equation, the shift is actually to the left. Similarly, if the shift is to the right, let's do it over here on the left side. If the shift is to the right, C is positive. In our formula, we would have f of x equals a cosine bx minus positive C. And when simplified, we would have f of x equals a cosine bx minus C. That means if we see a negative in the formula, we're actually shifting to the right. So let's take this from examples to an actual rule. Positive, negative equals left and right, respectively. This reverse engineering doesn't apply for the vertical shift. With the vertical shift, if you have a positive, you are shifting up, and if you have a negative, you are shifting down. Well, let's focus on some graphs where all we do is a phase shift. When we're done with that, we'll focus on some graphs where all we do is a vertical shift. And then we'll start putting it all together in different combinations. Maybe we'll have an amplitude and a phase shift, an amplitude and a vertical shift. And we want to just throw out as much practice as we can get applying each transformation. I'm going to go ahead and erase this. Draw myself a trigonometric graph. Use my standard labels. And for these examples, let's count 1, 2, 3, 1, 2, 3, up and down the y-axis. Okay, for our first example, we're going to go ahead and graph f of x equals sine x minus pi halves. What transformation have we applied in this problem? Negative pi halves is our phase shift. And so we are going to be shifting pi halves to the right. Well, my advice for you when you are graphing functions that involve more than just amplitude and period is to actually draw two pictures. The first, graph your function with the amplitude and period applied. In this case, amplitude of 1, period of 2 pi, standard graph. Then take that picture and apply your shift. This is going to help us try not to graph it all at once. Keep in mind, you should also be using your technology and getting an idea of what the picture will look like. So that's what I'm going to do now. Cover over that. Y equals sine of x minus pi over 2. Make sure my window settings are set to my x and y axis. I have a y min of -3, a y max of 3, an x min of 0, and an x max of 2 pi. 0, this is not set to 2 pi from my last example. Y min, I'm going to go ahead and make -4 because I like to overshoot by just a little bit. You don't have to overshoot if you don't want to. And then graph. Well, it turns out when you take a sine curve and shift it pi halves to the right, you actually get a negative cosine curve. And that's okay because sine and cosine come from the same values in the same order, just at a different starting point. So it's not surprising when we find out that one trig function shifted ends up being another. In fact, that actually sounds like a pretty good test question. Which of the following shifts to sine will produce a cosine curve? Anyway, let's go ahead and graph this. I'm not going to start my picture with my final answer, but I know in my mind what my final answer should look like. I'm going to move this to the side, and I'm going to graph a sine curve with an amp of 1 and a period of 2 pi. Sine starts at 0, ends at its period, has a midpoint halfway in between. Sine goes up, and sine comes down. Well, to have a shift of pi halves to the right, I need to take each of the 5 critical points and move it pi halves to the right. In order to do that shift accurately, I need to know how big pi halves is. I can see from my choice of scale that pi halves is 1 tick mark. If you're using the graphing paper provided, you would say that it's 1 box away. I'm going to take each point and move it 1 box to the right. From 0, 0, that gives me pi halves 0. From pi halves comma 1, I get pi comma 1. From pi comma 0, I get 3 pi over 2 comma 0. And from 3 pi over 2 comma -1, I get 2 pi comma -1. Connect your new points in as continuous a curve as possible. After the original point, sine went up, came back down, bottomed out, and came back up. Go up, come back down, bottom out, and then we can't come back up because we're off our grid. Notice though, now that I've shifted to the right, I kind of have this gap. So what should this bottom part of the sine graph be? Well, if you're looking at your original, we know sine is continuous. So once it reaches the end, it would start again. And if you were to go backwards, it would go backwards, which means we need to get 1 more point by going down to the minimum at 0, -1. It's going to be my expectation that you will fill the grid you are provided, whether you have labeled it yourself or I have provided the labels for you. This is the complete graph. Bring back my technology, and I can see that it matches. Let's do another phase shift problem. For these next examples, I actually want to use the graphing paper. This is the large blank trig graphing paper that you'll be expected to use on an assessment. That way you can practice scaling based on the size of the boxes or number of boxes and labeling your x and y axis to fit your graph. Now I'm going to continue with my same scale, and I'm going to do this for every problem. I'm going to say pi, 2 pi, 3 pi halves, 1, 2, 3, -1, -2. And I'm going to keep labeling them this way. I might even go so far as to put a negative pi halves and a negative pi in the other direction, because I know that I'm going to be shifting my curves left and right, and I want to be able to fill the entire grid. So after pi, -3 pi halves, and -2 pi. Well, I'm going to continue to follow my own advice. 1, to use technology and know what my graph should look like when I'm done. And 2, to graph 2 pictures. 1 that does the amplitude and the period, and then 1 that handles the final result and the shift. With that in mind, let's take a peek at what cosine x minus pi thirds should look like on our scale. Cosine x minus pi thirds. Graph it. My scale is the same setting that I had before, although this time I might change my window to match. Let's just take a look at what that would do. -3 to 3. Now I'm using the exact same window. And as you can see, my point doesn't start at 0, 0, but it doesn't also start at the exact peak, which is why the hand graphing is so important. I'm going to put this to the side, and when I'm done drawing my picture, hopefully I'll see this as my final result. Let's start with a basic cosine graph. Cosine starts at its amplitude, ends at its amplitude, and has a minimum halfway in between. Connect these with a dotted, curved graph, making sure to cross the x-axis at exactly the 1/4 mark and exactly the 3/4 mark. Now take this graph and apply the shift. What kind of shift is this? This is a phase shift of pi thirds to the right. That means every point on my graph needs to go pi thirds to the right. Well, I didn't label my graph with pi thirds. How big is pi thirds, and how can I determine exactly how far I need to move my graph? Here's what I usually apply. If I know that 3 boxes is pi halves, I can take pi halves and divide it by 3. That will tell me that 1 box is pi sixths. Well, if 1 box is pi sixths, 2 boxes must be 2 pi sixths, which simplifies to pi thirds. I now know that a shift of pi thirds is 2 boxes to the right. Take your first point at 0, 1, move it 2 boxes to the right. It's now pi thirds, 1. Take your point at pi halves, 0, move it 2 boxes to the right. It's now, where is it? Take a pause, and you can use your calculator to do this. What is pi halves plus pi thirds? We've reviewed this in class before, but let's review it here in the calculator. If I want to do pi halves plus pi thirds without getting an irrational answer, I'm going to type 1/2 plus 1/3 and then hit enter. Crazy decimal, not irrational, but a crazy decimal. Hit math, select fraction, and I find out that that point is at 5 pi sixths. This ordered pair is 5 pi sixths, 0. Another way is that you know this is pi. You know 1 tick mark is pi sixths. This is pi sixths before pi. I'm fine any way you figure out these points as long as you figure out their exact location. Let's keep going. 2 to the right, Is pi thirds after pi, or 4 pi thirds? From 3 pi halves, 2 to the right is 11 pi 6. And then this point is off the graph, so I have completed to the right. I do have space over on this side. Just for posterity, I'm going to fill my whole graph. Keep my original curve. Finish it going the other way. And take all these points and move them pi thirds to the right. Don't worry about labeling them. We're just moving these points so that we can draw a more accurate picture. The more dots that I have to connect, the cleaner my graph is going to appear. From this point, swoop down, down, up. From this point, and there we go. Well, let's compare my final answer to what I had predicted with my calculator. Do these look approximately the same? And the answer is yes. I have successfully graphed cosine of x minus pi thirds. This time, I'd like you to try the next example before I do. Pause the video here, see if you can sketch a graph on your own. I hope you paused and tried this before the answer. Let's go through this problem. Notice I added a little monkey wrench. This graph has been flipped. It still has an amplitude of 1. It still has a period of 2 pi. I'm still using the same skill on my graph. I also notice that it has a phase shift of pi fourths to the left. With that being said, let's take a look at what this will be from our calculator. In your calculator, type negative sine x plus pi fourths graph. This is going to be like the last one, where I can tell this didn't start at 0, 0, and it also didn't start at a peak like cosine would. It's actually somewhere in between. But at least I have an idea that the soup should start low, go high, and end low. Table that for later. Give yourself a plain sine graph with just the flip. Remember our first one, we want to do the amp and the period without the shift. So I know sine starts at 0, ends at 2 pi, midpoint in between. Normally I would go up to 1 and down to -1, but because it's negative, I'm going to go down to -1 and then back up to 1. Take this graph and shift it pi fourths to the left. Just like last time, we have to ask ourselves, well, how big is pi fourths? Since pi fourths is 1/2 of pi halves, it must be 1/2 of 3 boxes. I'm going to go ahead and label all the pi fourths that I've memorized from my unit circle. And I know that a shift of pi fourths to the left is the equivalent of 1.5 boxes to the left for every ordered pair. Since I'm shifting to the left, I'm actually going to start on my rightmost point. Move this 1.5 boxes to the left. Because I went ahead and labeled all my pi fourths, it's very easy for me to see that the new ordered pair is 7 pi fourths, 0. The top point is at 3 pi halves. When I move it 1.5 boxes to the left, it becomes 5 pi fourths, 1. My point at pi, 1.5 boxes, 3 pi fourths, 0. My point at pi halves, 1.5 boxes, pi fourths, -1. I'd like to continue my curve through the whole graph, so I'm going to continue my original through the whole graph. Peak, half, peak, back to the beginning. And I'm going to take each of these points and move them a box and a half, a box and a half. I'm no longer doing this to label exact values, just to get a more accurate curve. Follow the shape of your original graph and connect your dots. And then let's just double check our answer. Does our new graph look about what our window had predicted? It goes down, up, down. We've completed the graph. All right, let's take a look at our next phase shift example. For this one, we've introduced a frequency of 2, which is going to change our period. Because a frequency of 2 is not a significant change, I'm going to go ahead and continue labeling my graph the same way that I've been labeling it so far. This time, I'm actually going to go ahead and list all of the key features that we've talked about. Amplitude is 1. The period is 2 pi over 2, or pi. Phase shift. Now we need to be careful here. The phase shift is pi to the left, but with a frequency of 2. So the phase shift is actually pi over 2 to the left. We're going to need to adjust our phase shift to fit the frequency of the problem unless it's already been factored out for us. Let's draw a cosine curve with an amp of 1 and a period of pi to get our baseline graph. We know that cosine starts at 1 and ends at 1, and since the period is pi, we actually need to end at pi. In the middle, it hits its negative, and so I'm going to go ahead and sketch halfway our original cosine curve. And I am going to take it all the way to the end of the graph. Frequency of 2 means 2 cosine curves to one end of the graph. Since I needed it last time, I'm also going to finish my cosine graph going in the other direction. To finish the picture, I need to shift pi halves to the left. How big is pi halves? Thankfully for me, pi halves is actually part of my scale. I know that pi halves to the left means 3 boxes to the left for every point. Because I'm going to the left, I am going to start my shift at the very end of my graph. Here's my first ordered pair. Go 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. From here, I'm just starting to use the pattern that I've already established to fill out the rest of the points. All right, let's label our 5 key or critical values. This point is 0, -1. This point is pi fourths, comma 0, pi halves, comma 1, 3 pi fourths, comma 0, and pi, comma -1. Connect your dots in as continuous a curve as you can manage. If you'll see, I've run out of specific points, but I've established a clear pattern and I'm pretty confident in my ability to finish it. One thing that I did not do with this example was plan ahead. So hopefully when I graph this with my calculator, I'm going to see that I graphed it correctly. 2x plus pi. Same scale as before. And you can see it matches. We've just graphed an example using both a period change and a phase shift. Let's do a fun example next. This is one of the more unusual examples when our frequency is a value or a multiple of pi. What it ends up doing is giving us a really interesting graph that has an unusual scale. So reviewing our information, the amp of this problem is 1. The period is 2 pi over pi, or 2. And the phase shift, now notice how this is written. As you can see, the pi has already been divided out from the phase shift. In the previous example, it was not. In this example, you see the factored form. This -1 is the shift. It's already been adjusted to accommodate the frequency, which is why it's in parentheses and the frequency is out of the parentheses. So a phase shift of -1 is a shift of 1 to the right. Well, with a period of 2, that means I need to finish the entire sine curve at 2, which means I can't, or I can, but I shouldn't label my axis in terms of 2 pi. If I put 2 pi right here, 2 pi is approximately 6.28, and it's not a scale that's convenient for graphing a sine curve whose period is 2. Instead, I'm going to relabel my graph so that the last point is 2. That means the midpoint is 1, 1/2, and 3/2. Compare this with the scale we used before. By dividing out the pi, I'm using the same values just without pi. Amp of 1, I'm going to go ahead and graph a sine curve with an amp of 1 and a period of 2. And then I'm going to shift everything 1 to the right. Now be careful, not 1 square, but an entire value of 1. 1 is actually worth 6 squares. So this is going to be a pretty big change. I'm going to extend my graph going the other direction to give me a few more points to work with. All right, every point needs to go 6 boxes, or 1 to the right. Starting at 0, go 1 to the right, 1/2, go 1 to the right, 1, go 1 to the right, and then here I've run out of room and I've only graphed a half of the graph. But again, if you recognize the pattern for sine, for every up curve, you need to have a down curve, or you can start from these points and move them 1 to the right. Here we go. And then I'm out of points, but at this point, I know what the sine curve is supposed to look like. Label 5 critical values: 0, 0, 1/2 -1, 1, 0, 3/2 1, and 2, 0. And I've completed my graph. Last one with intense focus on phase shift. This example has it all. It has amplitude, it has period, it has phase shift. Try this one out on your own. Go ahead and pause the video here. All right, let's get graphing. You may or may not have noticed, but this one has a negative right here. So this one is flipped with an amp of 3, a period of pi, and a phase shift of pi/2 over 2, or pi/4 to the left. I'm going to go ahead and graph a sine curve with an amp of 3 and a period of pi. If you remember, sine starts at 0, ends at its period, midpoint halfway. This one needs to go up to 3, back down to the middle, down to -3, which you can see my whoops. We really should scale our graphs so that they fit on the grid. And then I'm going to keep that going because there is going to be a shift, and I'm going to need as many points as I can get to accurately shift this picture. Down below. Here we go. Let's shift every point pi-4ths to the left. And I really like doing pi-4 shifts because I can just go in and add all the pi-4ths labels, and it really makes figuring out where the point or the ordered pair is easy. From my first point at 0, 0, I need to go 1.5 boxes to the left. That's going to be -pi-4ths, 0. From my maximum, which is originally at pi-4ths, if I go to the left pi-4ths, I'm at 0, 3. Pi-halves, go to the left, becomes pi-4ths. 3 pi-4ths, go to the left, becomes pi-halves. Pi to the left becomes 3 pi-4ths. And at this point, I've got my 5 critical points. I no longer need to label my ordered pairs. I just need to make sure that I'm going to create an accurate picture. So I'm going to continue shifting my ordered pairs to the left. And then I'm going to connect the dots in as continuous a curve as possible. And then we can assume from here that it is going to go up again and peak by 2 pi. You should fill your graph, but we're just going to pretend like this part doesn't exist and be happy that we managed to graph 2 full rotations of sine on our grid. That's it for phase shift. Let's take a look at vertical shifts going up and down. Same thing, more graphs. For our next example, we're going to take a standard sine graph and move it up 3 units. I'm going to follow my same advice as before, and I'm going to draw a standard sine graph. This one has an amp of 1 and a period of 2 pi. I'm going to graph this as a dotted function, and then I'm going to shift that function 3 units in every direction. When you're doing a vertical shift, there are 2 things to note. This 3 is outside of the function's parentheses. If there were going to be parentheses in this, it would be around the input, and the 3 is not within those parentheses. In order for a shift to be horizontal, it needs to be grouped with the input of the function. Anything outside of that is considered vertical. So this is a vertical shift, which we will notate as VS. Because it's positive 3, I know that it's going up 3. Okay. When you're labeling your graph, my period being 2 pi means that I can label my x-axis the same way that I've been consistently doing. Keep in mind, if you're going to be using a period of 2 pi, I did provide graphing paper that's already labeled to 2 pi. These blank graphs are better used when your problems have varying periods and you need to change the picture to suit that. When you're graphing your y-axis, you want to plan ahead. If my amp is 1 and I add 3, I'm looking at a new maximum of 4. I'm going to need to make sure that my y-axis reaches 4. So I'm going to label 2, 4, -2, and -4. With that being said, let's graph a standard sine curve. Amp of 1 means go to 1, back down to 0, back down to -1, back to 0. Take that graph and shift everything up 3 units. So 0, 0 becomes 0, 3. Pi halves 1 becomes pi halves 4. Pi 0 becomes pi 3. 3 pi halves, comma -1 becomes 3 pi halves, comma -2. And 2 pi becomes 2 pi comma 4. When you graph things with a vertical shift, we need to introduce this idea of a midline. During the first part of the lesson, we talked about the critical values being the x-intercepts, the maximum, and the minimum. Well, the max and min are still the max and min, but what was previously an x-intercept is no longer on the x-axis. When referring to trig functions, the key features aren't always going to be standard key features. In fact, our x-intercepts are no longer going to be called x-intercepts. They're instead going to be referred to points on the midline. The middle of a trig graph is where we want to think of as critical. So these former x-intercepts are now points on the midline. And I am so glad I drew that midline. You may have noticed this error right when I did it. I'm just now noticing it. This point should have been at 2 pi 3. There we go. Let's check this with our calculator. Y equals sine x plus 3. Delete, 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 delete. Graph. Oh, I did not fix my window to match my new scale. This new graph goes up to +6 and down to -5. Let's adjust our window settings. Still 0 to 2 pi, but now my new y min is -5 and my new y max is +6. Now does this graph look like my graph? And the answer is yes. Let's try another one. For the next example, we're going to graph negative cosine x, but shift it down 2 units. To begin, graph a negative cosine x. And let's plan ahead. I believe the same y-axis scale that we used before will work, but I know the amp is 1, which means the highest value is +1 and the lowest value is -1. If I subtract 2 from that, subtracting 2 from a lowest point of -1 gives me a lowest point of -3. So the same scale I used on the last example of 4 will work for this example as well. Graph a standard cosine curve that's been flipped as a dotted line. Cosine typically starts at its amplitude. We will start at negative amplitude and end at negative amplitude. Peak exactly halfway in between. And then take all of these ordered pairs and move them down 2 units. 0, -1 becomes 0, -3. Pi halves 0 becomes pi halves -2. Pi 1 becomes pi -1. 3 pi halves 0 becomes 3 pi halves -2. And 2 pi -1 becomes 2 pi -3. Connect your dots in as continuous a curve as you can. And it may help you, and I always recommend drawing your midline. Let's check if we graph this correctly. Y equals negative cosine x minus 2. Looks good. Let's graph another example. For this example, there's an amplitude and a vertical shift. Amp equals 2, period is 2 pi. Vertical shift is down 2 units, like before. Plan ahead. My amplitude tells me a max of 2 and a min of 2. If I subtract 2 from that, I need to make it to -4. Will the scale from before work? Yes. Up 2, 4, down 2, -4. Draw your sine curve with just the amplitude and period. Shift every point 2 units down. 0, -2, pi halves 0, pi -2, 3 pi halves -4, and 2 pi -2. We've just completed another picture. At this point, we simply need to practice every variation on this that we can. So for our last problem together, we're going to graph a function that has amplitude, period, phase shift, and vertical shift all at once and see if we can handle a multitude of transformations. F of x equals 3 cosine (3) x minus pi 6 plus 1. Try this problem on your own. Pause the video here. For the sake of consistency, I've decided to use the same scale on this graph that I've used on every graph so far. This will allow you to see the effect that the transformations have on the function. Let's go over the key information. We have an amplitude of 3, a period of 2 pi over 3, a phase shift of pi 6 to the right. Keep in mind, this pi 6 has already been factored away from the frequency. We do not need to divide by the frequency in order to find the phase shift. Finally, it has a vertical shift up 1. I'm going to follow the advice that I've used all through the examples, and I'm going to graph a cosine function that has an amp of 3 and a period of 2 pi thirds. Then I'm going to shift that graph pi 6 to the right and 1 up, point by point. Now I may have done myself some favors and used a scale more suited to 2 pi thirds. As you can see, I went to 2 pi, and on this scale I haven't even labeled a 2 pi thirds, let alone be able to graph to it. But the graph paper I've chosen as our printable graph paper is actually in groups of 3. And there's a very good reason why we've always had 3 squares in between each tick mark. Pi halves is 90 degrees, 30, 60, 90, 120, 150, 180. By using groups of 3s, we've actually done a graph that has the entire unit circle on it. And to help me graph this function, I'm going to label every box with my unit circle. Pi 6, pi thirds, pi halves, 2 pi thirds, 5 pi 6, 7 pi 6, 4 pi thirds, 5 pi thirds, and 11 pi 6. It's a little crowded, but it's going to be worth it when I'm needing to label these points exactly, and I'm going to be able to see exactly where the point lies. Now, cosine starts at its amp and ends at its amp. If the period is 2 pi thirds, that means my function needs to end at 2 pi thirds. Start at 3, end at 3. Halfway in between, cosine reaches its minimum. And halfway in between each min and max, cosine has its intercept. I'm going to go ahead and draw my first cosine curve. The nice thing about this scale is that I'm hitting a critical value every tick mark of the graph, so I can quickly and easily sketch the remainder of the graph by hitting a critical value every square. To reinforce the meaning of frequency, I have managed to complete 1, 2, 3 cosine curves when the frequency was 3. From here, I'm ready to do my shift. I'm going to shift every single point pi 6 to the right and 1 up. Based on this scale, pi 6 is 1 square. So really, I'm shifting every point 1 square to the right, 1 square up, and labeling it. Because I took the time to label every tick on the graph, it's very easy for me to find each ordered pair. 1 to the right, 1 up, 1 to the right, 1 up, that says pi halves -2. You can't really see it, but it's there. 1 to the right, 1 up, 2 pi thirds, comma 1, and 1 to the right, 1 up. 5 pi 6, comma 4. You only need to label 5 critical values, but from here I'm going to continue 1 to the right, 1 up, in order to give myself an accurate picture. The more points I have to connect, the more likely I am to keep my curve in the right position. Go ahead and connect your dots. I'm going to pretend that the left side of the axis is in here, but I do want to connect my picture back down to the origin to complete the graph. We haven't spent some time doing domain and range recently, so let's identify the domain and range of this example. Domain for a cosine and sine graph is always infinity to infinity, but this graph has been shifted and has an amplitude. What's the new range of this function? This new cosine ranges from -2 to 4. Where's the midline of this function? The midline is halfway between each minimum and maximum, or where most of my critical values have landed. So the midline of this function is y equals 1. Let's check our graph in our calculator. Make sure you use that extra pair of parentheses when you type it in. There's a double parenthesis here before the +1. My scale stayed the same that I used the last time, so I shouldn't have to change my window. And I'm going to go ahead and graph. Does this look like what I sketched? You've now completed part 2 of the video notes for Objective 4, Graphing Trigonometric Functions. Please practice these skills and be ready to ask questions next time we meet in class.